Good morning, everyone. Today, my colleague Kundan and I, Achala, will be presenting a webinar on unleashing the power of large language models with OpenAI GPT. I would like to commence this presentation on large language models by addressing the question of what they are. Large language models represent a groundbreaking innovation in the realm of artificial intelligence and natural language processing. These models are built upon extensive training with colossal datasets, equipping them with a profound capacity to comprehend and generate human language. Their significance in today's technological landscape cannot be overstated, as they have the potential to revolutionize numerous fields, from enhancing chatbots' conversational abilities and automating content generation to aiding in complex tasks like medical diagnosis, etc. Large language models stand at the forefront of innovation. In this presentation, we will delve deeper into the intricacies of LLMs, exploring their architecture and capabilities. So, some of the most well-known language models today are based on the transformer model, including the generative pre-trained transformer series of LLMs by OpenAI and the traditional bidirectional encoder representation from transformers called BERT. So, some of the most influential models that we use today are GPT-3, GPT 3.5, GPT-4, Lambda, Llama, Palm, 5 stable LM, etc. Now that we have explored what LLMs are and their significances, let's dive deeper into a specific powerhouse within this realm, GPT 3.5. GPT 3.5 Turbo is an advanced language model that builds upon the capabilities of its predecessor, GPT 3. With its exceptional text generation and understanding abilities, GPT 3.5 Turbo is a versatile tool for various applications, from chatbots and content generation to natural language understanding tasks. Its proficiency in generating coherent and contextually relevant text makes it a valuable asset for businesses. Coming to its details, it can handle around 4,000 tokens at a time, and OpenAI says it is double than what the tokens what GPT-3 could handle.
Yeah, Achala, maybe you can speak a bit louder.
Yes, sir, sure. In the next one. Having talked about GPT 3.5 and its capabilities, it is now essential to delve into the core components that underpin the functionality of large language models. One of the fundamental building blocks is tokenization. Tokenization in large language models is the process of breaking down a continuous stream of text into smaller units, known as tokens. These tokens can be as short as the individual character of a word or as long as words or subwords. This step is crucial in natural language processing because it enables LLMs to analyze and understand text by segmenting it to discrete units. Thus, it allows these models to work with text at a granular level, making it easier for the model to generate coherent and contextually relevant responses. Now, after knowing that we have covered tokenization, another vital aspect of the fundamentals of large language models is word embeddings. In the context of large language models, word embeddings are like the building blocks of language understanding. The embeddings are numerical representation of words that capture their semantic relationships. They enable LLMs to associate words with meaning and context, allowing the model to comprehend the intricacies of language and generate coherent text. For example, if we consider uh, the picture given here, good morning is converted to the respective word embedding. So the given text is converted to a numerical representation that is understandable by the computer. Next.
So audience, feel free to ask questions. Let's keep it very interactive. And those who are not speaking at the moment, kindly mute yourself.
Now, let's explore how this word embeddings operate within large language models. delving into two essential architectures, which is recurrent neural networks and transformers. Recurrent neural networks, or RNNs, are a type of neural network that can memorize the previous output when receiving the next input. In contrast to the traditional neural networks, where inputs and the outputs are independent of each other, RNNs are particularly useful when it's necessary to predict the next word in a sentence because they take the previous word into account while generating the next sentence. Hence, the context of the topic will be maintained. The key feature of RNN is the hidden state vector, which retains the information about a sequence. This memory allows the recurrent neural networks to keep track of information that has been captured. But RNNs can be computationally expensive, and they struggle to handle large input sequences. As the length of the input sequence increases, the initial information may get diluted through multiple copies, causing a decline in its predictive accuracy, and this problem is known as the vanishing gradient problem.
So, Achala, there was a question on word embedding. Did we cover that slide or it's coming up?
Sir, it's done.
Yeah, somebody wanted a clarification on that.
Yes, sir, sure. What exactly was there doubts, sir?
They wanted you to explain the word embedding slide, I think.
Okay. So, word embeddings are basically where each textual aspect is converted into a into its numerical representation. So, they help the system capture the semantic relationships between the words. So, how exactly they are associated with respect to their meaning, and that the large language model. Hello.
Yeah, I think the
Yeah.
question is how do you assign those numbers? See, basically, that's just an example. You have to give some number. So you can say the time is 2 or something, mode is 8, right? So you can give some numerical encoding because machine learning only understands numbers, not words. So
Yeah,
every
there
word is
are
treated as a number.
various ways of doing that, like one hot encoding, pipe pair encoding, etc. So, with respect to GPT models, the method they use is generally pipe pair encoding. So, there are multiple methods that LLMs use. This is, as Vivek sir said, this is just an example of how the text is converted to word embeddings. Any other doubt with respect to word embeddings? Okay. So, in order to tackle the vanishing gradient problem, the LSTM architecture was introduced. So, in the LSTM architecture, it is also a type of RNN, but we tackle the vanishing gradient problem with the cell mechanism. So, this cell mechanism selectively stores and discards information in its hidden state. So, it has the LSTM architecture has three main gates. One is the input gate that manages and updates the information. The forget gate decides what information has to be ignored or to be omitted, and the output gate controls the output. Thus, this prevents the diluting of the information. This approach enhances information retention from the start of the sequence. Later on, the transformer architecture was introduced in a 2017 Google paper, which will now be explained by Kundan.
So introducing the transformer model. So the transformer model was one of the most exciting developments in the field of machine learning. It was initially introduced in the paper "Attention is All You Need" by Google. Uh, Transformers can be used to write stories, essays, poems, and answer questions also. And we have seen in the news that large language models were even able to pass exams that were hard for humans. So, transformers are basically a powerful type of deep neural networks that excels in understanding context and meaning by analyzing the relationships in sequential data, such as words in a sentence. So, the name transformer comes from their ability to transform one sequence into another. One of the major reasons why transformer made made such a huge buzz is cause unlike vanilla RNN or LSTM network, the vanilla RNN had a short window size and hence couldn't capture long-term dependencies. Whereas LSTM model, the subsequent models such as LSTM or GRU had a bigger window size when compared to the vanilla RNN. Although they had a bigger window size, they weren't still able to capture that many long-term dependencies as we take suppose we take 4096 tokens as told before. The model wasn't able to capture the complete context within the given frame. So given enough computing power, transformer has the ability to have an infinite window size. Hence it is one of the novel approaches that made such a huge impact in today's world. So this is the actual original transformer architecture, which was given in the Attention is All You Need paper. I know it seems a bit tough, but let's break it down into simple components and understand this. So let's take an example of machine translation. So machine translation is the process of using AI to automatically translate text from one language to another without the human intervention. So it takes the sentence as an input and output its translation as the output. So now let's break down this transformer block into see what's inside it. So inside the transformer, we can see an encoding component and a decoding component and a connection between them. So the encoder component is a stack of encoders stacked upon one another. Here we have shown only a single encoding component, but in the real life example, there are many encoder layers stacked upon one another. And the decoder component is a stack of decoders with the same number as the number of encoders. The encoders are all identical in structure, but this shouldn't be confused with the fact that they share the same weights. Although they have the same structure, they do not share the same weights. Uh, so to understand this encoder and decoder, let's see what's inside them. So the encoder component has basically two layers: the self-attention layer and the feed-forward layer, where the decoder has three layers: the self-attention, feed-forward, and the encoder layer, decoder layer, which is sandwiched between them. Uh, so before we give the input to the transformer, we perform word embedding. As Achala told before, I guess you have understood what word embedding is. So we first pre-process the given sentence by performing word embedding, and then we perform something known as positional embedding. Now, unlike RNNs, transformers do not have the inherent ability to understand the sense of order of the given input sequence due to their attention mechanism. We'll get to what attention mechanism in a short while. So basically, the positional embedding is used to provide the model with the information about the position of words in the input sequence. So now after we perform this, okay, in the original attention is all you need paper, to perform this positional embedding, the authors came up with a clever idea where they performed, where they used the sign function to embed the words in the even index, and they use the cost function to embed the input sequence in the odd index, as shown here. So here, POS denotes the position of the word, and I denotes the dimension of embedding, while D model says the size of the word or the token embedding. So as we perform the word embedding and the positional embedding, we take a sum of these two embeddings, and then we give it to the transformers encoder block. So the input flows through the self-attention layer. So now what is self-attention? So self-attention layer is a crucial component of the transformer since it enables us to consider the relationship between the words in a sentence. When the encoder processes each word, it doesn't just focus on the current word, whereas it looks at other words in the sentence too. So the self-attention allows the model to assign different levels of importance to different words in the encoding while encoding a specific word. So this helps the model capture dependencies between the words regardless of their distance from each other in the sentence. So as you can see in the original architecture, you can see here something known as a multi-head attention in the first block. So the multi-head just says that there are several heads of the attention block, each trying to capture different aspects of an input sequence, such as the syntax, semantics, and the different relationship between each word. Now, to achieve this self-attention, we basically input the given input into three distinct fully connected layers. which are the query, key, and value. So the query, key, and value comes from the retrieval system. I hope you know what a retrieval system is. If not, let's take an example of YouTube. So for example, when you type a query to search for some video on YouTube, the search engine will map your query against a set of keys associated with the videos in the database, then present you the best matched video. So in the attention mechanism, we take the dot product of the query and the key to get a score matrix, which tells us how much focus should be put on a given word with respect to the other words in the sequence. So the higher the score, the more the focus is basically. Then we take these scores and then scale them down by by dividing them by the square root of the dimension of query and key. This allows us to have stable gradients. Then we send these scaled scores through the softmax to get attention weights, which are usually in the probability range of 0 to 1. Then we multiply these attention weights that we get by applying the softmax with the value vector to get the output vector. So then we feed this into a linear layer. As you can see in the original, just a second. Yeah, as you can see here, we feed the output of the multi-head attention through a add and norm block. You can also see that there exists a residual connection which adds the output vector with the original position input embedding, so as to maintain the positional knowledge within the sequence. So the output of this residual connection is then normalized. This process is done so as to avoid the effects such as exploding or vanishing gradient. After this is done, we basically pass the input, I mean the output of these two blocks into the feed forward network. So as I guess some of you know what a feed forward network is. So the output of this attention layer is basically passed on through the feed forward network. So the feed forward network is a set of fully connected layers that perform complex transformation on the information received from the self-attention layer that helps capture patterns and features that are consistent across the entire input sequence. So to sum up the encoder block, we basically take a given input sequence, we perform word embedding and positional embedding, then pass it to the multi-headed attention where we capture the different aspects of the input sequence, such as syntax and semantics or relation between words. Then we add the recurrent residual input and then normalize this output, and then we pass it to the feed forward network. Then we this in the feed forward network we capture the different patterns and features, and then again we pass it to the add and norm block. Then we get the encoder output. Now, moving on to the decoder block. Okay, the decoder is designed to generate the target sequence one token at a time, while taking into account the context from the input sequence. I believe anyone who has used ChatGPT would know that the model basically generates just one word at a time. This is because the decoder was designed to generate just one target token at a time. So the decoder also has both self-attention and the feed-forward network, but between them is the encoder-decoder attention layer that helps the decoder focus on the relevant parts of the input sequence. Okay. One of the main differences between the self-attention in the decoder layer and in the encoder layer is how they operate. The self-attention mechanism operates slightly differently from that in the encoding phase. So in the decoding layer, the self-attention layer basically allows the decoder to consider words that have already been generated in the target sequence. This helps the model to generate content within the given context. Whereas in the encoder layer, we are giving the entire input to the self-attention layer and to generate, to understand the context. But in the decoder block, the self-attention layer only receives the already generated input. Uh, Basically, it is made to remain in the given context of what it is generating. Next, moving on to the encoder decoder attention layer. This is also called as the cross attention layer. So this is used to focus on relevant parts of the input sequence while generating the output. And the feed forward network is works similar to the one in the encoder layer. Then the output of this. Okay, I forgot to mention that each of these outputs is passed through a add and norm block so as to normalize and have better gradients and to avoid the vanishing gradient problem. The output of the entire decoder block is then passed on to a softmax layer to get the output probabilities and to choose the one, the output which is most probable to occur, and that is given as the output. And that is, fed back to the decoder layer so as to generate the next output. So to sum it up, let me just show an example. So yeah, as you can see, the same machine translation task here. So first we take the input, we perform word embedding, then we perform the positional embedding, then we pass it to the encoder block where it is encoded into an input vector. Now this input vector is given to the decoder. Now the decoder performs the decoding operation and basically passes to the linear softmax layer and then is used to produce the output one token at a time, which is then fed back to the decoder to produce the next output. Okay, I request Achala to take over from here.
So friends, let's ask questions so it becomes more interactive. You can speak up as well.
So one thing is
Hi,
that
Kundan. Yeah,
Yeah,
sorry.
hello.
Yeah, hi. So myself, Shruti. I just have a query here regarding the cross attention layer. So as you can see in the cross attention layer, we're feeding the output from the encoder into the decoder attention layer, right? But if
Yeah.
you see, it's a sequence to sequence uh, um, attention that happens in the decoder attention layer.
Yes.
So it's like the system does not know has any input about what is coming in the past. What is coming in the future, but it has some knowledge on what was there in the past
Yes.
words,
Yes.
right?
Yes.
Previous words. But in this case, when you're feeding the entire encoder output, doesn't it get all the knowledge? So how does the cross attention actually work here? That is my confusion.
Okay. So the cross we give the okay, the cross attention is not given the entire input. It's just given just the embedding to know like what part should it focus on. We are not giving the we are giving the embedded output from the encoder. We are not giving it the entire sequence, right? We are first embedding it into, we are encoding it into a vector representation, and that vector representation is given here. So the encoder decoder attention is only used to focus on the relevant parts of the input sequence, just to remain in the context, not to just by heart the whole thing and produce an output.
Got it. But in the self-attention layer, say for example, my name is so and so. When my and name
Okay.
is passed, Shruti won't be there. Whereas in the encoder decoder attention layer, you will have the embedding for the name. And when the subsequent, there is an arrow mark that passes from self-attention to encoder decoder attention. So what does that
Yes.
infer? Like what happens there? If you have the
um
embedding values for all and you are passing only my name, then how does it, why
okay,
is
just
the
let me clarify. In
cross-attention
the
based?
self attention, I specifically told that this in the self attention layer, I just give the already generated input. I'm not giving the entire input here. I'm giving the already generated. Say okay, let me just show the slide. Okay, see, when I is generated, I give I back to the decoder. I'm not giving I am student. The whole thing. I'm not
Right,
giving the whole
right.
thing. I'm giving the
Yeah,
already generated input to back to the I mean already generated output back to the
correct.
decoder, so that it.
Yeah.
Sorry.
So my question here is, say for example, you have passed I am, okay? So I
Okay.
am passed through so over here, decoder is a black box you have mentioned, whereas I'm breaking it down into the layers. When I am
Okay.
is
Okay.
passed to
Okay.
the self-attention layer, it tries to predict the next word, okay? So next
Okay.
word prediction is the self-attention layer's job here. So it tries to
Yes.
predict the
Yes.
next word. Then when it passes to the cross-attention layer, over there it has all the embeddings. So after I am, it predicts a. But when this I am a is passed to the cross-attention layer, what happens there? It already has the embeddings of all the words that it has received from the encoder, right? So how does it behave there? Like what happens between both of them is my question.
Okay. This is a specific, machine translation task. So, the one I've given as an input is converted into encoding representation of that language. So when I give it here, uh, it basically takes the input embedding and tries to match it with what I have. So the I am is encoded into something. So the self attention layer is just to maintain within the context. It is not already having something else. It is just to say that this is the context being I am is the context. I have to predict what's next. So the the embedding that is coming from the encoder layer, that tells it what it should generate next, not the self attention layer. The self attention layer just tells us what is the context being generated right now, not what it has to generate. What is it, the context that has been generated? So it basically combines these two and then gives output to the softmax layer.
I think what it does is it takes the previous decoded uh, vector that is there, and it also uses the all of the encoded encoders representation, and then it predicts an context vector, which then the decoder again uses it. So so
Yes.
so whatever the previous decoded things is used, it's that, and it also uses the all the encoded side of vectors, and then it does the same like the key value I mean the query key. In this case the query is this decoded thing, right? And then it uses the same query key approach to get the value, and in this whole case the key and value are the same actually. But anyway, so it basically generates that context vector from the encoder side, and then that context vector is passed to the decoder back.
Okay.
It's a
Yeah.
combination. It's a combination of what encoder gave me plus what I have done so far. So it's a
No, wait, it's a
combination.
combination of what decoder gave you and everything in the encoder. Encoder has
Correct.
the,
Correct.
yeah.
Correct.
Okay. Yeah, I think I got clarity. Thank you. Thank you.
And also, I just want to mention that GPT is not an encoder decoder, right? It's only uses decoder.
Yes,
Yeah,
yes.
it's a decoder sequence. Yeah.
Someone else had a doubt, I believe. Okay, moving on. I request Achala to take over.
Now that Kundan has explained about the intricate architectures that are used in the large language models, taking the generative beauty and transformer series as the models we'll be talking about today. So the GPT series comprises of GPT 1, 2, 3, and 4. Talking about the first three series, these three, generative pre-trained transformer series have significantly advanced the field of language generation. Starting off with with the first model in the series, that is GPT-1. It pioneered the series with impressive language understanding and generation capabilities. GPT-2 took a giant leap forward in terms of model size and quality, whereas GPT-3, with its 175 billion parameters, demonstrated unprecedented text generation capabilities. So the table below shows the key differences between these models and how each model kept improving over its predecessor. Now, after having known about GPT 1, 2, and 3, let's shift our focus to the latest milestone in this remarkable journey, which is the GPT-4 model. The GPT-4 model is the latest iteration in the GPT series. Its key feature is not only its massive 200 trillion parameters, but also its versatility in handling different type of inputs. Unlike GPT-3, 2, or 1, it not just handles text inputs, but it also processes various inputs like images and other multimedia content. This multimodal capability allows it to comprehend and generate content that combines both textual and visual elements. For example, if we give it a load an image with a car for the model to generate a caption, it will generate a caption with respect to what was present in the image. Thus, take multimedia inputs and give outputs accordingly. So this makes it a very valuable tool for tasks like image captioning, as I mentioned, and content generation across mediums. Furthermore, GPT-4 showcases marked improvements in factual correctness, reducing instances of hallucinations or factual errors, thus enhancing its reliability in generating accurate content. With its robust language understanding and extensive fine-tuning options, the ability to handle different data types, GPT-4 stands out as the forefront of AI language models.
So, Achala, in your research, they have not published the image to text part of it. Am I right?
No, sir. We found. Sorry, sir. Could you repeat your question?
The GPT-4 was supposed to also be multimodal input, which means images also with text. But I haven't seen verbiage whether they have actually released that part of GPT-4, which does image to text. Have they?
Yes, sir. When I was going through OpenAI's website, they have released a version where they have loaded image with a person sitting in a car along with a chair attached to it, and he's ironing. That was a typical example used on all the websites. The GPT-4 model generated a caption that it's a person who's attached to a car and an iron stand is attached to it, and he's ironing his clothes. So yeah, the model was capable of generating image captions.
I see. Okay.
So now we will learn how exactly the GPT-3 model works.
So the GPT-3 model was trained on 300 billion tokens of text with the objective to predict the next word. So we could take an example of as given here, a robot must dash. So initially the model might give a robot must eat or robot must destroy. So some labeler who will tell the model that this is wrong, and he gives the correct statement that a robot must obey. So that is we basically calculate the error between those two outputs, and we try to retrain the model so as to get the actual GPT-3 model. So the ChatGPT model that we are using today is a variant of the popular GPT-3 model. So the ChatGPT was basically modified and improved using both supervised and reinforcement learning methods with the assistance of a human trainer. So the let's tell this human trainer as labeler here in our context. So there basically includes three steps. So the first step is called as supervised fine tuning of GPT 3.5 model. The second step is reward model. And the third step is proximal policy optimization, also called PPO. So in the first step, the a pre-trained GPT is model is used, and it will be fine-tuned with the help of the labeler by creating a supervised data set. Now the input queries were actually collected from actual users, and the model generated different responses with respect to each of the input prompts. Then the labeler then wrote an appropriate response to each of these input prompts, just to see to get they just wanted to see what the prompt is going to answer. Then the GPT-3 model was then fine-tuned using this new supervised dataset to create the GPT 3.5 model. Next, we move on to the step two. In after the SFT 3.5 model, that is the supervised fine-tuning model that was trained in the step one, the model generates better responses to the given any input prompt. So in this step, the SFT model is used to generate different uh, responses for different prompts. Like they were used to generate 4 to 7 responses for a given prompt. Now, the labeler determined a reward for each of these outcome, and this reward was proportional to the quality of response that was generated from the initial prompt. So the labeler ranks the output in a sequence of best to worst. Then we can use this data in order to train a reward model. So the input for a reward model will be the user's prompt, and one of the responses that were generated by the output generated, and the output will be a scalar value which determines the quality of response with respect to the input prompt. Also, we use a ranking that we generated in the past in order to train the reward model. Next, we move on to the step 3, that is the proximal policy optimization, PPO. So in this step, we pass some unseen input sequence to clone the SFT model we got in step 1. Then the model will generate responses with respect to the input prompt. We then pass the response to our reward model, which we got in step 2, to understand how high quality was this response for that input prompt, and the output reward will be used to fine tune the parameters of our SFT model. So this is how our SFT model will incorporate, more human-like characteristics and behavior through reinforcement learning. Okay,
So
coming to the
Kundan,
use.
on that
Yes, sir.
slide, I
Yes,
think
sir.
step 2 and 3 both are part of the RL process. So
Yes, sir.
even step 2 is the beginning of the RL process.
Yes,
Step
sir.
3 is the conclusion of the RL process. So RLHF, as we call it, right?
Yes, sir.
So
Yes, sir. Yes.
step 2 is also part of RL. It's not separate.
Yes, sir. It basically is the reward model. So yeah,
Yeah.
it is a part of this.
Okay.
Okay, coming to the use cases of GPT, one could generate content to, for blogs that we write these days, blogs and, web pages too. And translation, as I showed right now, like translating from one language to another without, human intervention. Then you could use it to write codes. Suppose you're a beginner who is trying to learn coding, you could use it to write code. And you can also use it to debug your code, although the models, although they give most of the answers are right, but sometimes we have faced the problem of it not debugging it right. Then it can be used for code completion too. It can be used for code documentation. Suppose someone wants to write a cleaner code of what they have written, it can be GPT can be used for that. Then as we have seen these days, most of the large companies use their AI customer service instead of manual labor. Then one can use it for personalized learning. Say you want to learn something at your own pace, and you want to have a interactive session, but you don't have the ability, amenities to do so. You can use GPT. You can ask the most silliest questions to GPT, and you can get the right answers there. And you can use it to language to learn a new language. And GPT also has a ability of interactive storytelling. And although the creativity is not that great, but you give it some initial sequence, it generates a very good sequence. So now I request Achala to
No,
demonstrate a use.
so I was just off the cuff comment here. I was looking at this list.
Okay, sir.
This is really exciting for me because this means, and this is just a sample, and each of these
Yes.
could have many other use cases below them. So we are looking at a couple of thousand product ideas here. Okay. So, I mean, that's what we are saying, the generative AI revolution, right? So using this technology, you can fundamentally alter so many business use cases. And these are some of them, and below each of them, there are countless more, sub use cases. So we are looking at a massive set of product ideas. And within CellStrat, with our new Imagine GPT product platform, that's what we are trying to encompass, where we'll have a few of these, launched as easy to use for business clients. Okay, go ahead. That was just a comment.
Oh, yes, sir. So I request Achala to show the real-time application implementation of the chatbot.
So, as Vivek sir just mentioned, there are a lot of products that can be developed with the multiple use cases of GPT. These are just a few. So, we have done a simple implementation of how GPT can be used to revolutionize business. Kundan, is my screen visible?
Yes, yes.
Okay. So I would love this is a simple implementation of how we use GPT in the context of a financial AI bot. So this code demonstrates how we can leverage GPT's language capabilities to generate a conversational assistant for financial related queries. So firstly, we import the two libraries like
Can
OpenAI
we
for
just
connecting to
increase the font a notch or two notches?
Exactly.
Is a control plus if it is Windows.
Or you can just zoom in the website.
It's a minor matrix not happening.
Okay, that's okay. You can continue.
So sorry. If this is more better.
Yeah.
Yes, clear.
So yeah, so this code here demonstrates how we can leverage GPT's language capabilities to create a conversational assistant for financial related queries. We start off with importing the two libraries, OpenAI for connecting with the OpenAI GPT and the Gradio, which is interface for our chatbot. So we have to first start. We start off with setting up an OpenAI and the system message. So we first set up our connection to OpenAI. How exactly we do this is we provide our OpenAI key to access the GPT model. Then we define a system message that sets the context for our AI assistant. So as we see here, the message we have put for us AI bot is, you are a financial AI assistant with expertise in real estate, stocks, bonds, and money. So since we have the context here as a financial bot, this would be our system message. It can change with respect to different applications. So then we come to the custom GPT function. Here, the custom GPT function takes the user input as a parameter and uses it to create a conversation. So we start with the system message and then we append the user message. When they use OpenAI's chat completion API, when we use the OpenAI chat completion API to get a response from the assistant based on this conversation, finally we extract the assistant's reply from the API's response. Then we move on to how we put this out on we show a interface for the chatbot. So we have, as mentioned before, we use a Gradio library for that. So to make our chatbot more accessible and user friendly, we use Gradio. So this interface simplifies the interaction with our model. So here we set up our Gradio interface. It uses the custom GPT function as its core, and it specifies that it takes the text inputs and produces text outputs. So we have titled our bot as finance bot. So when we run, we get a link. So when we click on this link, it opens a new web page which will have interface as shown below here. So now if I ask my finance bot, what are stocks? It gives a response. We can ask company-oriented questions too. So, giving different contexts, we can generate different bots for different types of companies or different industries based on different domains. This was just an example. So, yes, ma'am.
Hi. So Shruti here again.
Yes, ma'am.
How are you? Do you see any latency issues, or how are you tackling latency issues here? Like, if you see the response is not very instant, right? It takes some time.
Yes, ma'am. It took much longer. So we use parameters like presence penalty 0.5, frequency penalty 0.5, etc. to reduce the amount of time taken. We could also limit the number of tokens we can generate, but if we could put a parameter as maximum tokens is equal to 100 or 1000, that will give a response within 2 or 3 seconds. But the problem we would face with respect to that is, even though we get an immediate response, the response would not be complete. It would just end with like the first paragraph or first 1.5 paragraph. So
Right.
TensorFlow, this was the best output that we could get with respect to complete output by these parameters, that is presence penalty, frequency penalty, etc. So this was the best we could get with respect to this now. So we are trying that we get a better output with respect to the latency, and we are working on it.
Got it. Any information on how GPT-4 is performing in with respect to latency, and have we tackled this issue in the recent release version?
We haven't worked with GPT-4 yet, so I generally have no idea. But I'm sure that these latency issues are being covered in GPT-4, as it's been trained on more parameters, and multiple issues that were present in GPT-3 has been tackled there. I'm sure that this would not be an issue in GPT-4. If I had run the same model maybe with GPT-2, it would be much slower. So yeah.
Okay, got it. Thank you.
So Achala, you are calling it a finance bot, but really it's really just a basic use of the GPT API, right? So, you have not really fine-tuned or found a fine-tuned version of the GPT. Am I right?
Yes, sir. We have to work more extensively on that. But if when we were working with this bot and I asked it, like, how do I improve the stocks of my company? So it gave a response like, as your finance AI bot, I would do so and so to improve the stocks of your company. So it would not particular be a finance, but it would at least assist us in that context. That as your finance bot, I would expect you to do so and so.
Even Core GPT has generalized internet intelligence, so it will answer common questions on every domain, in fact. But let's say I wanted to ask, can you recommend bonds from New York municipal bonds market, which ones will outperform? So that, I think, something more specialized it may not do, but generalized internet intelligence it has. So
Yes, sir.
yeah.
It's a very basic demonstration of how we
Yeah.
can use it in different business domains.
Yeah. No, this is good. Very good presentation and demo. Lots of basics. Audience, any other questions?
So you haven't used any prompts here as well, right?
Sorry, ma'am, can you repeat?
Have you tried using prompts?
Prompts for the bot, ma'am?
Yeah, currently.
It
Just
will give the same response as what ChatGPT would give.
yeah. So no, I'm asking, are you streamlining it on any custom data or using any prompts? Have you tried
No,
any?
ma'am, no, ma'am, no, ma'am. It generates the same output what ChatGPT would give, so it would train on the same data. We haven't custom trained it on specific data as such.
So we have a customer actually in CellStrat who's in the business of bond research in New York. So they have sent us some data on bond transactions which have happened in the past. They asked us to train a custom chatbot where they could ask questions on bond research. So that did need custom handling through LangChain, and mining the table of bond data, and then the IPO prospectus of bond. So the next level of innovation of product development is, how do you fine tune a very remarkable GPT LLM or Llama LLM on custom data corpus? So that's where the things stand today. A lot of business opportunities being created around that particular concept. And we haven't even started talking about images and audio and video. So I think it looks very exciting times ahead.
Yeah.
So Achala and Kundan, are you done?
One more question.
Yeah.
Achala, how have you restricted that this would answer just for finance related queries? Like if I ask
Uh,
anything else, like what are the top 3 recommended movies, will it give the reply for that?
yes, sir, but I think it would still be limited to 20 September 2021's data. It won't give the latest update.
Okay, but it's not restricted to finance, right?
No,
Just
no. It's not restricted.
that's it.
Yeah, this is Chat GPT, right? So it can answer anything up to September 21. Whatever information was present on internet, it can talk to it.
Got it.
So one of the product innovation we are trying to do, and many others, combine that GPT intelligence with current information, because it will just answer till September 21. And if I wanted stock research or movie research as of today, it can't. So we have to call Google API or Bing API, and through maybe a LangChain process, combine that intelligence with historical intelligence and answer it. So there's huge amount of product innovation possible here. Any other questions, folks?
So Vivek, I have a question for you.
Mm-hmm.
Since I'm also intensively working on these LLMs and other things, I see that you were mentioning about one of your clients asking for bonds and etc. So, how are you taking care of data privacy here? I see using OpenAI, many people are concerned about data, though there are a lot of articles saying that that shouldn't be a concern since Microsoft has taken over a part of it. But aren't
Yeah,
you
good
focused
question.
on
I mean,
LLMs?
even this particular client, it's a small firm in New York which does bond research. So they also had the same concern, interestingly. But we have told them we are using GPT API. They are okay with it for now, but the concern remains. And one of, again, a big set of product innovation, which we are doing in our product Imagine GPT, that we are trying to create an equivalent Llama 2 architecture. So we'll give two options to each client, where we'll say, if you want best of breed LLM capability, you let us call GPT API. But if you want privacy, as a foolproof guarantee, then we'll have to use a second best, which is the open source LLM. In this case, Llama 2 is the most popular nowadays. So that will not send to any GPT. So even this client had this concern, but so far they are okay with us calling GPT.
I think most of the companies are doing this. Even we have already started fine-tuning our Llama model as well.
Yes, yes. So I understand that 8 out of 10 companies in Fortune 1000, list are concerned about data privacy. I think 80% of Fortune 1000 companies have a contract with OpenAI to use this technology, but they are just doing some POCs. So 80% of the total set of large companies do want a more of localized. So a lot of innovation and research remains how to get to private controls.
Right. Vivek, just one request is probably next time, how do we, even though we fine tune a model, so my next vision, I think most of them would have this, is how can we leverage the real time data? So you could have fine tuned it, but you need to keep updating your system with the real time data as well if you're fine tuning it, right? How can that be handled effectively? Can we have some session related to that in the future? Right.
My understanding, I've been in AI for 5 years now. So in AI, you have to keep retraining the models because data is a moving target, right? So you have to every quarter, every 6 months, every year, you have to update the AI model because new data has come into the system, and which may be new kinds of data. So you have to retrain the model. I mean, I don't know how else to bypass that. Uh, the only thing Bing Chat was trying to do was that they were combining the Chat GPT intelligence, which is historical, with Bing's current search capabilities. So I haven't used Bing Chat. I don't know how good it is. So these are all R&D areas and a lot of exciting times for all of us.
Okay, thank you.
So we in CellStrat are looking for not only full-time hiring of AI scientists for our new product development initiative. We are also wanting community contributors in the Imagine GPT product team. So if you have the LLM chops, reach out to us, and we would like to see if you can contribute to our product development activity. And also we have one or two open positions as full-time hiring positions as well. So, any other questions for Achala and Kundan today? Okay, so in that case, thanks a lot, Achala and Kundan. Very well done. A very good understanding of grasp of your basics. Transformer is very hard to explain, neural network. and even I have struggled with it over the years. So very well done, and thank you for your presentation. Look forward to your next set of programs. Audience, thank you for joining, and we'll see you later. Have a good day.
Thank
you,
you.
sir.